Picture a train the size of a bus, 12 meters long, 22 tons of steel and iron, and it is balancing on a single rail no wider than the edge of a ruler. Nobody is holding it up. There are no outriggers, no second track, no wires from above. And yet, it just sits there, perfectly level, as if the laws of physics had quietly agreed to look the other way. Then it starts to move. It rolls into a curve, and instead of leaning outward and flying off the way you'd expect, it leans inward into the turn all by itself. No driver touched anything. This really happened. The year was 1910. The machine was called the Brennan monorail, and to the people who saw it, it looked less like engineering and more like a magic trick. So how did it work? How do you keep a 22-ton train upright on one thin rail when a parked bicycle can't even stay up on two wheels? That's the question we're going to answer today, and the answer is one of the most beautiful pieces of engineering you've probably never heard of. Let's start with why anyone would want this in the first place. By the early 1900s, trains ran on two rails exactly like they do now. Two rails work. They're stable. So why would a sane engineer try to remove one of them? Because two rails are expensive. To lay a railway, you need twice the steel, twice the labor, twice the land cleared and leveled. A man named Louis Brennan looked at that and asked a simple question. What if a train only needed one rail? Cut a railway's track material roughly in half and you make railways cheaper to build across whole countries. And there was a second prize. A train balanced on a single rail could lean into corners like a motorcycle does, which meant it could take those corners much faster without being thrown off. One rail promised cheaper railways and faster trains at the same time. There was just one small problem. A train on one rail falls over. Of course it does. Balance a broomstick on one line on the floor and it topples instantly. So Brennan needed something inside the train that could fight that fall. Something that could push back against gravity continuously, forever, without a human doing anything. And he found his answer in a spinning wheel. To understand what he did, you need to understand one strange object. The gyroscope. A gyroscope is just a heavy disc spinning very fast. That's it. But when a disc spins fast enough, it develops a stubborn personality. It really does not want to change the direction it's pointing. Spin a disc quickly, and it fights to keep its axle aimed at the exact same point in space. This resistance has a name: angular momentum. You felt a small version of this. A spinning bicycle wheel is weirdly hard to tilt in your hands. A spinning top refuses to fall until it slows down. A football thrown with a tight spiral flies straight. In every case, the spin is holding the object steady. That's angular momentum, keeping its word. Now here's where the gyroscope gets genuinely strange, and this is the part you have to hold on to for the rest of the video. When you push on a spinning gyroscope trying to tilt it, it does not tip the way you pushed. Instead, it slowly rotates in a completely different direction, turning sideways to your push. Engineers call this precession. Push it one way, it swings another way entirely. It sounds like it's breaking the rules. It isn't. It's just angular momentum redirecting your force around a corner. And there's a flip side to precession that Brennan built his whole train on. If you force a gyroscope to precess, if you deliberately twist it sideways, it responds by tilting up or down. Push the spin sideways on purpose, and the disc lifts or drops in return. Hold that thought, because it's the secret of the entire machine. A gyroscope trades one kind of motion for another. Twisted here, it pushes there. Brennan realized that if he could control which way the gyroscope tilted, he could control which way the whole train tilted. The spinning wheel could become the hand that holds the train upright. So he built a small model. A little flywheel and electric motor to spin it, tucked inside a toy-sized train on a single rail. And at first it worked beautifully. Every time the model began to tip to one side, the gyroscope precessed and shoved it back upright. The train stood on its one rail like it was glued there. Brennan must have thought he'd cracked it. Then he tried to make it go around a curve, and the whole thing fell apart. Here's why. The gyroscope's entire job is to keep pointing the same way in space. That's its nature. That's the whole reason it can balance anything. But when the train drove into a curve, the train turned, and the gyroscope stubbornly refused to turn with it. It kept facing the original direction, like a compass needle that won't budge. From the train's point of view, the gyroscope was suddenly twisting sideways inside it. And remember what a sideways twist does to a gyroscope. It makes it tilt. So the gyroscope tilted, which meant it tilted the train at exactly the wrong moment, and the model rolled off the track. The very thing that kept the train up on a straight line knocked it over on a curve. Brennan needed a fix. And the fix he came up with is so clean, it's almost funny. He added a second gyroscope. Then he spun it the opposite way to the first. Two identical wheels side by side, one spinning clockwise, one spinning counterclockwise. He connected them with a gear so that whatever one did, the other was forced to do a mirror image of it. Now watch what happens on a curve. The train turns. Both gyroscopes stubbornly want to keep facing straight ahead. Both get twisted sideways by the turning train. But because they spin in opposite directions, their unwanted tilts are exact opposites too. One tries to tip the train left, the other tries to tip it right with equal force, and equal and opposite forces cancel. The two wheels quietly agree to hold each other in check, and the train sails through the curve still perfectly level. With that solved, Brennan was ready to stop playing with models. He was going to build the real thing. A full-size monorail big enough to carry actual passengers. This is where the story gets much heavier. Literally. The prototype he built was about 12 meters long, roughly the length of a city bus, and it weighed 22 tons. Inside sat two enormous gyroscopes, each spinning at 3,500 revolutions per minute. That's fast. Fast enough that the outer edge of those discs was moving at hundreds of miles an hour, sealed inside the machine. And scaling up revealed a brutal new problem the toy never had to face. In the little model, the only thing that gyroscopes had to fight was their own behavior on curves. But a 22-ton train has a different enemy: gravity. All that weight is constantly, patiently trying to tip the train over and pull it down onto its side. And the moment the train leans even slightly, its center of gravity shifts out past the rail and gravity's pull gets stronger, which makes it lean more, which makes the pull stronger still. It's a trap that feeds on itself. Brennan discovered that the gyroscope's natural gentle precession simply wasn't strong enough or fast enough to win that fight. On a toy, a soft correction is plenty. On 22 tons, a soft correction is useless. The train would start to go, and the slow, natural push couldn't catch it in time. So Brennan had his key insight, the idea that separates a clever toy from a real machine. Don't wait for the gyroscope to precess on its own. Force it to precess. Force it harder and faster than it ever would naturally. Remember, forcing a gyroscope to twist sideways makes it push back with a tilting force. So, if you deliberately twist those gyroscopes fast, they'll shove the train upright with real power, far more than their gentle natural correction ever could. Brennan stopped asking the gyroscope politely for help. He started giving it orders. First, he took care of the basics. He hooked the gyroscopes up to a petrol engine to keep them spinning, and he sealed each one inside a vacuum-tight casing. The vacuum matters. With almost no air inside to rub against, there's barely any friction, so the wheels keep their speed with very little effort. In fact, they held their spin so well that even if the engine died completely, the gyroscopes would keep turning for up to 30 minutes before the train was in any danger of falling. Half an hour of safety from nothing but stored spin. Now for the hard part. How do you force those gyroscopes to precess at exactly the right moment, in exactly the right direction, every time the train wobbles, with no human in the loop? Brennan's first attempt was mechanical and direct. He let the axles of the gyroscope stick out and rest between two guide plates fixed to the train's frame. The idea was simple. When the train tipped, the axle would press against one of the plates, and the friction would make it roll along the plate like a wheel on the ground. That rolling forced the gyroscope to precess quickly and shoved the train back upright. It worked, but it wasn't smooth. Every bump in the rail sent a vibration through the machine, and the axles would bounce and rattle against the plates instead of rolling cleanly. The correcting force came out jerky and uneven, never quite proportional to how far the train had actually leaned. For a machine whose whole promise was a ride so stable passengers wouldn't feel a thing, jerky wasn't good enough. So Brennan threw the guide plates out and designed something far more elegant. This is the heart of the machine, so let's take it slowly, one piece at a time. He bolted the gyroscopes firmly to the train's frame so they turned with the train. When the train tipped, the gyroscopes began to precess naturally, just a little, the way they always want to. But this time, that tiny natural movement wasn't doing the heavy lifting, it was just the trigger. The axle of the right-hand gyroscope was linked to a small rod, an actuator. As the gyroscope precessed, it nudged this rod. The rod worked a lever, and the lever controlled two valves, and those valves controlled something powerful: compressed air. Here's the chain of events, step by step. The train leans. The gyroscopes precess a little. That tiny precession pushes the actuator rod. The rod flips a lever. The lever closes one valve and opens the other, and suddenly a blast of compressed air is released down a pipe. That air rushed into one end of a large tube running through the center of the system. Inside that tube was a sliding gear rack sitting between the two gyroscopes. When the compressed air flooded in and the pressure rose, it shoved that gear rack sideways, and the gear rack meshed with the gyroscopes forced them to precess hard in the direction that would push the train back to level. So follow the whole loop. The train starts to tip. The gyroscopes feel it and give a tiny twitch. That twitch opens a valve. The valve unleashes compressed air. The air drives the gear rack forces the gyroscopes to precess with real power, and that powerful precession hauls the entire 22-ton train back upright before it ever leaned far enough for a passenger to notice. The result looked like a genuine miracle. The monorail was so stable that you could take every single passenger and crowd them onto one side of the carriage. All that weight heaved over to the edge, and the train would not tip. It just stayed level, calmly correcting for the lopsided load as if nothing had happened. In 1910, at an exhibition in London, Brennan drove 50 passengers around a circular track on a single rail. One of the people who climbed aboard and rode it was a young Winston Churchill, who became an enthusiastic supporter. Think about what that crowd was seeing. A 22-ton machine on one rail, leaning into its turns, refusing to fall even when loaded unevenly, all balanced by two spinning wheels and a puff of compressed air. For 1909 and 1910, this was astonishing. It really did look like the future of travel had arrived early. So here is the real mystery. If it worked this well, why are you not riding one to work tomorrow? Why did the self-balancing train vanish from history? It wasn't because the engineering failed. The engineering was brilliant, and everyone could see it was brilliant. It failed for reasons that had nothing to do with whether it worked. The first reason was timing. By 1910, two-rail railways were everywhere. Thousands of miles of track, countless stations, workshops, train crews, a whole industry built around two rails and decades deep. To switch to monorails, a country would have to rebuild almost everything from scratch. Brennan's train was better in theory, but the world had already spent its money on the old way, and it wasn't about to start over. The second reason cut deeper, and it lived inside the design itself. Every single carriage needed its own set of spinning gyroscopes to stay upright. On a normal train, you have one locomotive pulling 20 simple, cheap, dumb wagons behind it. On Brennan's system, every wagon would need its own gyroscopes, its own engine to spin them, its own delicate balancing machine, all maintained and kept running perfectly. Because the day the gyroscopes in a carriage stopped, that carriage would simply fall over. A train that needs flawless machinery in every car just to stay standing is a hard thing to trust with 100 passengers. And that fear, the fear of the gyroscopes failing, was ultimately what stopped it. Investors looked at this beautiful, balanced machine, and instead of seeing the future, they saw everything that could go wrong. They kept their money in the two rails they already understood. The project quietly ran out of support, and the self-balancing train rolled into a museum instead of into history. But don't feel too sorry for Louis Brennan. This monorail wasn't even his most influential invention. Years earlier, Brennan had designed a torpedo steered from the shore by wires guided to its target from a distance. Many call it the world's first practical guided missile, a weapon so valued that the British military bought it and installed it to defend harbors across the empire. And later in life, he poured years into building an early helicopter. The same man who made a train balance on one rail also helped invent guided weapons and flying machines. Brennan simply saw the world differently than everyone around him. So the next time you watch a train roll by on its two ordinary rails, remember that it didn't have to be this way. For a brief moment in 1910, a man proved that a train could balance on a single rail, lean gracefully into its own corners, and stay standing even when you tried to knock it over. All thanks to a spinning wheel that pushes sideways when you shove it, and a breath of compressed air that turned a train's own falling weight into the force that held it up. It worked. It really worked. The world just wasn't ready to rebuild itself around it. If you enjoyed uncovering this one, consider subscribing, and we'll keep digging up the brilliant machines history almost forgot.